talk to you about this work on galaxy mergers that we've been doing in my group for the last decade or so now, with this extended list of collaborators. So the motivation for many people to study galaxy mergers is that in our hierarchical picture of structure formation, galaxy mergers are one of the principal ways of building up mass. So by merging together two galaxies, you build up mass in many ways. You build up the stellar mass, which is the obvious luminous component that we see in this process. But you also build up the gas mass in the galaxies, the dark matter mass, and also the black hole mass in the center. Because just as the galaxies merge, so eventually do the black holes at their center. So many people are interested in mergers from this structure formation perspective and also as cosmological products. But that is not what I'm going to be talking about today, not what I'm going to be focusing on. Instead, I'm going to be focusing on what galaxy mergers do for the internal properties and characteristics of galaxies during and soon after their interaction. And I would argue this is just as important as the role of mergers in structure formation. So this is a cartoon from a relatively old paper now by Phil Hopkins that summarizes many of the characteristics that undergo change or are predicted to undergo change during a galaxy merger. So the way to read this plot is we have this kind of cartoon picture going counterclockwise here, or clockwise in terms of the way that we think the interaction process will act, and then some results from the simulations that this paper focused on in the center. So the idea is that if you have galaxies in close proximity to one another, they have a close enough passage, then they can tidally interact. And the first evidence that we might see of this are these very well-known tidal features, so tails and shells. Then when the galaxies coalesce, you can trigger a starburst. And so if you look at the star formation rate of these mergers as a function of time, you can see a peak at first passage, but you can also see large peaks in the star formation rates when the galaxies fully coalesce. Then we also have these predictions that you can trigger an AGN. And this is because the same process that triggers star formation can also funnel gas all the way down onto the black hole and light up the black hole as some form of AGN or quasar. This feedback that we get from the star formation and the AGN can potentially remove the gas from the galaxy, so it can heat the gas up. It can either fully remove it or it can ionize it, put it up into a hot halo, so it is no longer available for star formation, and so then we end up with these red and dead elliptical galaxies. So potentially mergers are not only important for triggering star formation in AGN, but maybe eventually truncating it. So we would like to be able to test these theoretical predictions, and that's what I'm going to be talking about maybe today. So the bread and butter data set that we have used for this has been based on the Sloan Digital Sky Survey, with other multi-wavelength complementary data sets that we've added into it. So we have two components to our main data set, because what we'd like to be able to do is trace this merger process through time, going all the way from the widely separated pairs all the way through to the fully coalesced galaxies. So the first component of the sample that we have been using is a sample of close spectroscopic pairs selected from SDSS. So both of the galaxies have to have a spectroscopic redshift so that we can make a selection both in projected separation, kiloparsecs on the sky, but also so that we can make a velocity cut, because as best as we can, we want to be able to remove chance projections. So we make a number of cuts, and we have this fairly large sample of galaxy pairs to work with. As Chris said in his introduction, one of the really important components of any observational work is to make sure you have a robust experimental design. And for this work, we're going to be wanting to compare various properties like star formation rates between these merger samples and non-merging samples. So we have to have this control sample for non-mergers. So the way that we do this is for every galaxy that is in a pair, so for every merging galaxy, we look at the pool of non-merging galaxies, so that's essentially the rest of Sloan, so some 650,000 galaxies in Sloan that don't have a close companion. and we find all of those non-merging galaxies that have the same redshift, the same stellar mass, and are in the same local environment. So the same kind of group environment. We typically have hundreds of controls matched to each galaxy, and then we can look differentially at their properties. The second part of the sample, beyond the pairs, then is the post-merger sample. So these are now single galaxies where they have been identified visually in galaxy view by their very strong and obvious tidal features. So I'm not sure how well it shows up on the projector, but these galaxies all have really obvious shells and tidal features. These are the kind of ultimate train wreck. So this sample is much smaller. It's only around 100 galaxies. So the statistics are not as good as for the pairs. When we have control samples that we make in exactly the same way for this. So now we're ready to dive in and start testing those theoretical predictions. So we'll start off by looking at that first prediction, which was that we should expect morphological asymmetries. Now, this is something we already have a good sense is going to be true, because we know just by looking at images of galaxy mergers that they have these features. But we can do this quantitatively as well. So we've measured the asymmetries of the pairs sample in a computational way, in a quantitative way, using a code called GIM2D, which was developed by Luc Simard, and Luc has this morphology catalog, which he published back in 2011, with a number of different morphology metrics, including an asymmetry measure. So the way that I'm going to be presenting most of the results today is showing you plots of the projected separation of our pairs sample, which you can think of as a proxy for time during the merger. And then on the y-axis, there'll be some metrics. So in this case, it's asymmetry, but we'll also look at star formation, we'll also look at AGN. And always, this is going to be a differential measure. So the y-axis is always going to be comparing the pairs sample, the post-merger sample, relative to the control. Okay, sometimes it'll be linear, sometimes it'll be log, but there'll always be this dashed line showing you, if I were the same as my control, this is where I would be. So starting off with asymmetry, what we see is that at the widest separations, the morphologies are very similar in our pairs and in the control. And then as we get closer and closer in, we have this excess of asymmetry as the galaxies become more and more disturbed. So we have this nice rising trend. Now the post-mergers are not on this particular plot because they were deliberately selected to be morphologically disturbed, so it's not really a very fair experiment for the post-measures. So just the pairs on this plot. So this first prediction that we get disturbed morphologies gets a check. Next up, we can look at the changes in star formation rates. So we measure the star formation rates from the Sloan spectroscopy. And so now in this figure, we have again the projected separation. Now there's this additional gray box at small projected separation, and this is the post-merger regime. That's where I'm putting my post-merger point. Now the y-axis is an enhancement in the star formation rate, and this plot is on the log scale. So if the mergers had the same star formation rates as the control, would be at this 0 line. So what you can see again is that we have this increasing trend, that we have an enhanced signature, this time in the star formation rate boost, as you get to closer separations. And that the boost in the star formation rate is the highest in the post-mergers. But it's interesting to look at the scale here. These are typically not massive starburst galaxies, they're not ULIRGs. On average, the typical enhancement in the star formation rate is only a factor of a few. So you do get these boosts, but the effect is relatively modest. Another interesting feature is that we still see enhancement all the way out to 80 kiloparsecs. When we originally made our sample, we thought, this was going to be plenty wide enough to return to the kind of field value, but that turned out not to be the case. So we actually redid the analysis with a much wider set of separated pairs. In fact, we put no upper limit on it. We just took every galaxy in Sloan. We found its closest companion, so we could go out to arbitrarily large separations. So look at the blue points here. Those are the results from Sloan. So our original data set only went out to 80 kpc, so that's the enhancement you can see there. But now as we extend out to wider separations, you can see that these boosts, although small, do extend all the way out to about 150 kpc. And galaxies spend a lot of time out at 150 kpc, so they come in, they have a close passage, they get their boost, and then they're moving out to apocenter. And so if you actually integrate the total boost in star formation out of these wide separations, it's quite significant. It's going to be 20 or 30% of the full budget of triggered star formation. I don't know how well you can see it. This particular pair is separated by 90 kpc, and there's a beautiful bridge going between it. So we eyeballed a number of these very wide separation pairs to convince ourselves that they truly were interacting and that we didn't have any strange effects going on. These are truly very widely separated pairs whose orbits just take them out to these very wide apocenter.
Yeah. So is there any way to separate this into the first info ones?
That would be so nice if we could do that. We tried. We thought, well, if they haven't yet had a pericenter, they're not going to have these strong tidal features. So we redid this analysis, separating out those where we could see tidal features and where we couldn't. And our expectation was that the star formation rate enhancement when we had purified the sample would go up, but actually it didn't really change. I suspect what's going on is that many of the ones that we threw out, because we couldn't see tidal features, do have tidal features, but the Sloan imaging is so poor that we just couldn't.
Sorry. And when you say enhancement, you're just comparing to the ones who are in isolation?
Exactly.
Have
so here, for
comparable
example,
properties.
So this star formation rate enhancement, so this would be 50% more than you would expect in your mass redshift environment matched control. It's good to clarify that because we're going to see several plots with these kind of sets of axes. All right, next up is the gas phase metallicity. So the mechanism responsible, we think, for the boost in the star formation rate is that when galaxies have these pericentric passages, they trigger non-axisymmetric structures, such as bars. These bars allow a torque, which can drain angular momentum from the gas and funnel it to the center. You build up your gas in the center, you trigger a starburst. This should also have an effect on the central gas phase metallicity, because you're taking gas from the outer disk, you're funneling it to the center. And because galaxies have abundance gradients, such that they're more metal poor at the outside, you're taking gas that's more metal poor, putting it in the center, so you dilute the gas phase metallicity. So again, using the Sloan fiber spectroscopy, which is probing the inner few kpc of the galaxy, we can measure the gas phase oxygen abundance to test this prediction. And it seems to follow what we expect from the simulations, which is that we have diluted metallicity. So now we have a negative offset. So the metallicities are lower than in the control sample. And again, this seems to be linked to the proximity of the galaxy pairs with the strongest signature in the post-emergence.
Just to go back to your previous plot, one more. Aren't the error bars on the y-axis too narrow, too small?
For what? Why do you expect them to
For
be?
example, if you go to 40 kiloparsec separation, the error bar on at delta SFR is so narrow, while in reality I would expect there's a mess there, and so you should have a big error bar.
So these error bars
Yes.
are sigma over root n, and there are lots of galaxies in here. So it's
Sure.
true that you get some galaxies with no enhancement, but yeah, this has the advantage of the sample size, so it's over the root n. Yes, so we see this dilution in the gas phase metallicity. An interesting side note that we still see diluted metallicities in the post-merger phase is that you could imagine that after these starbursts happen, you would re-enrich your interstellar medium and maybe go back up to normal metallicity, or maybe even be higher than you were to start with. So the fact that we still see these low metallicities indicates that we're probably catching these post-mergers relatively soon after they've coalesced, before they've had the chance to do that re-enrichment. And that's actually consistent with the way that we've selected them. To see these very dramatic tidal features that do eventually fade, we expect that we are selecting them probably within a few hundred million years. Okay, next up is whether or not we trigger an AGN. So for the aficionados in the room, you'll know that this is actually a very controversial point, whether or not mergers trigger AGN. I'm going to try and convince you that they are a plausible mechanism, which is not to say that they are the only plausible mechanism, but I'm going to try to convince you that at low redshift, mergers can definitely be a way of triggering AGN. And we do this experiment in two different ways. The first way we do the experiment is we take the merger sample that I've already described to you, so the pairs and the post mergers, and we count up how many AGN we have. Then we count up how many AGN we have in the control sample. We look to see if we have more in the mergers than in the control. So very simple experiment. There's a subtlety here, though, that you can select AGN in a number of different ways. So you can select it in the X-ray, you can select it in the radio, you can use optical emission lines, you can use mid-infrared colors. And it turns out that not all AGN are equal. You get different types of AGN when you select using those different multi-wavelength metrics. So let's start off with the optical AGN selection criteria, which is the most commonly used one when you're working with slow data because you have the optical spectroscopy. So we use this so-called BPT selection criteria, where we're looking at the ratios of different strong emission lines to tell us about the ionization state of the gas. So we can just label according to these thresholds in line ratios whether something is an AGN or not. What we find is that for our pairs, so here's our projected separation again, for our pairs we find there are more optically selected AGN than in our control, so here's that dashed line, and that excess increases as you get to closer separations in this quite nice, smooth way. And again, we see the peak signal in the post-mergers. So the post-mergers have about a factor of 3.5 to 4 more optical AGN than you would expect for the control sample. I think this is like a nice demonstration of a causal connection between the interaction and the triggering of AGN. Then you can do the same thing for mid-infrared color selection. So this type of selection is preferentially picking out dusty, obscured AGN. You don't get very dusty things when you look at optical emission lines, but you can get those obscured objects when you look at the mid-infrared colors. Now the y-axis here has a different scale. Let's just look at the post-merger point here for easy comparison. So whilst we see the same kind of qualitative trend, we see higher overall excesses for the mid-infrared. So this was first done in a paper by a collaborator of mine, Shabita Sajapal, who interpreted this as the mid-infrared AGN being those that are preferentially being triggered in the merger. So when you have the merger and it's pouring all this gas and dust onto the center, your black hole is more likely to be obscured, and so this is a much more effective way of finding the AGN triggered by mergers. On the other hand, if you select in the radio, and there's this particular selection metric called low excitation radio galaxies, if you select in the radio, you find no enhancement. Okay? Even though the 1 sigma error bar is kind of consistent with no enhancement. So whilst the mid-infrared and the optical selected samples both seem to have a component associated with merging, this is not true for the low excitation radio galaxies. So we concluded that these are probably triggered by a more kind of slow secular process. So this is the first test you can do. Start with mergers, count your AGN. But you can invert that experiment as well, and you can start with an AGN sample and then see how frequently your AGN are in disturbed host galaxies. So this is a piece of work that I just put on the archive last week, which is accepted last week, where we do this morphological classification in very deep CFHT imaging. It's 3 magnitudes per square arc second deeper than Sloan, and so you can really pick out those tidal features much more effectively. So what we do is we take an AGN sample, we again have a control sample, and we count how many of the 2 samples are either isolated, have a close companion but don't seem to be interacting yet, have a close companion and have a tidal feature, or a single train wreck. We count those for the AGN, we count them for the non-AGN control, and that's what the ratio is that you see here. So again, I've put to guide the eye this dashed line. So if AGN were in the same morphological host galaxies as non-AGN, the data points would lie along. But what you can see is that for both interacting pairs and host mergers, AGN are more frequently, by a factor of 2 or 3, AGN are more frequently in morphologically disturbed host galaxies. So you can do this experiment both ways, and you get the signals. So I would argue we have very robust evidence for a connection between AGN and mergers at a low redshift. As I emphasized before, this is not to say that all AGN are triggered by mergers, just that mergers can do the job for you. Okay, so let's come back to this diagram. So we've done a pretty good job so far. We have demonstrated an excess of asymmetries. We've demonstrated an excess of star formation of AGN. Now let's look at this prediction of what the merger might do to the gas content. So this was one step in this merger pathway that until recently had really not been tested. And yet it's really a key step if you then want to propose mergers as a way of pinching galaxies. So we needed to go out and make new observations for this. Because gas fractions are part of what you get from Sloan. So we started off with measuring the molecular gas fraction in a fairly small sample of galaxy pairs. So we had 11 galaxies in pairs that were selected according to these criteria, and we made observations with the IRAM 30 meter to measure the H2 content, so molecular gas content. Once again, we had a control sample, and we tried to be very careful about things like aperture corrections and conversion factors, which, you know, if I was talking to a mainly observational audience, they always ask about. A small sample, but nonetheless, we'll do the controlled experiment of measuring, again, differentially between the mass of molecular gas in our 11 pairs compared to the mass in the control sample. So because this is a small sample, I cannot really plot this as a function of projected separation anymore. I'm just going to show you a histogram of what those gas mass offsets are. So just look at the red histogram, which is for that pair sample. And what you can see is that relative to the dashed line, which is now a vertical dashed line rather than a horizontal one, these values are all positive. So not only is there no deficit of gas, molecular gas in these pairs, there is actually an excess by a factor of about 2 or 3. So that was a bit puzzling. And we thought, well, maybe this is small numbers, we need a bigger sample. So then we did a bigger sample, we went from 11 to 58, which was kind of cobbled together partly from different PI programs, some in the literature, some of our own new observations. And so here are now the distributions for this much larger sample. So we still see an offset in terms of the star formation rate. So this delta SFR has a positive value on average. Here is the difference in the molecular gas masses. So we actually reproduce the same positive offset, factor of 2 to 3 higher gas masses in these pairs, which also you see in the total gas fractions. But interestingly, the star formation efficiencies, which is a combination of the gas and the star formation rate tells you how quickly you would deplete your gas if you continued star forming at the same rate. This is normal because your gas mass is high, but so is your star formation rate. So you'll actually burn through your gas with about the same efficiency as galaxies that sit on the Kennedy-Schmidt relation. With this larger sample, we could also start to try to look at trends with projected separation. So the individual data points are on here to kind of keep us honest, so you can see that there is a large scatter, but there's maybe a trend of this enhancement in the gas mass at closest separations. So the molecular gas seems to be more abundant in the pairs than in the control. So then we thought, okay, maybe this depletion is not going to show up in the molecular gas. Maybe it's going to show up in the atomic gas. Because maybe what's happening is you have to feed the molecular gas reservoir to boost the star formation, which we know is going on. So maybe it's coming out of the atomic gas. So, okay, so then we went off and we measured the atomic gas masses. So then these are Arecibo observations of the H1. This we had to do in the post-merger sample rather than the pairs because the Arecibo beam is really big and you can't resolve close pairs. So we did this with the post-merger sample. We had about 100 galaxies that were a combination of archival measurements and our own PI sample. And again, we have a control so we can compare the neutral hydrogen gas fractions with the control. And so again, we're finding that these gas fractions offset from their control by factors of around. So not only do these things have more atomic gas, and they also have more molecular gas. So this left us a little bit puzzled, and if you're an observer and you're puzzled, you call up your simulator friend. You say, what's going on? So we had been working with Jorge Moreno and Paul Torrey on this suite of idealized merger simulations using the FIRE2 model. And Jorge had been using these to look at the way that different gas phases respond during the interaction. So this was a paper that he was finishing actually about the same time as we were doing our observational work. And so as a function of time during the merger, he was tracing the difference between the gas mass in his interacting pairs, and he also has a control sample, so it's set up in a very similar way to our observations. So these horizontal lines here are his excess relative to the control. And you can see that in the late stage mergers, which is where we were probing, there is indeed an enhancement of the atomic gas. It's not as big as we find, but qualitatively it's there. Also an enhancement in the molecular gas. So what Jorge's found in these simulations is that this all comes at the expense of the warm ionized gas. That's where it's been. So there is still abundant gas left in these mergers. And another thing that we looked at was how the distribution of this gas might change. So this is still with simulations. We'd like to be able to do this with observations, but we're not quite there yet. So this is work that's led by Man Hani, who's here this week. So Man took a simulation of just one merger, zoomed at high resolution to look at how the circumgalactic medium, so the gas around the galaxy, might be affected by the merger. So we knew from the observations and from Jorge's simulations that the total gas is still very abundant. Man was looking at the spatial distribution of that gas. And so what he found was that when the merger occurs, so again we have time here, the merger occurs here, you get these high covering fractions of hydrogen in the CGM because of the gas being pushed out to these large radii, and that enhancement in the covering fraction can persist for a number of gigayears. So it's quite a long-lived effect. And this is an effect that we see not only in the hydrogen gas, but also in the metals, which also are redistributed. So again, in that same simulation that Man had run, as a function of time, the change in the metallicity of the circumgalactic medium, you can see that it goes up. So this is a very effective way, mergers are a very effective way of redistributing both the hydrogen, but also the metals out into the sea. All right, so up until now, I have been talking about the integrated properties of galaxies. So either from single slope fibers or from integrated measurements of the gas using single dish telescopes. But we are now well and truly in the regime of being able to do this in a spatially resolved way. So with IFU spectroscopy, we can take not just one fiber, but we can place a bundle of fibers over our galaxy. So we get not just one central measure of star formation rate, metallicity, we can do it across the face of the galaxy. One survey that has been doing this that we have been working with is MANGA. So this is the Mapping Nearby Galaxies at Patchy Point Observatory. So this is part of Sloan 4, where they've had this very clever idea of taking individual boss fibers, bundling them together, and then placing them over the Sloan galaxies. So this is a survey that over its full duration will observe some 10,000 plus galaxies, and so we end up with these nice maps of all of the properties that we are used to having for just single fibers. So we can have distributions of star formation rates, velocities, ages, anything you want from the spectrum. So we first started playing with this data soon after the first data release, and to cut our teeth, the first idea that we had was whether we could use this kind of IFU spectroscopy to find binary, or I should say dual AGN. So this has been a bit of a holy grail in the literature, to try and find these really close black hole binaries that are at some point going to merge and give us these very loud gravitational wave signatures. But it's proven very, very difficult to try to find these close pairs of AGN. There's really only maybe 20 or so found. So we had an idea that maybe we could see this signature in the IFU spectroscopy. So what we did was we looked in the first data release of MANGA, which was about 1,500 galaxies, and we looked to see whether any of the galaxies had very red mid-infrared colors. If you remember, that was the signature I explained of very obscured AGN, so late stage merger. There was only one that had those very red mid-infrared colors, and this is it. So even by eye, you can see that there are two stellar bulges. So they're separated by about 8 kiloparsecs. So these are definitely not in a really interesting binary regime of parsecs, but it's proof of concept. And then what we did was we took the MANGA map. So each of these pixels is a spectrum. So we call these spectral pixels spaxels. And we color-coded them by where they lie on this BPT selection diagram. So if the spaxel is on this wing, it's dominated by radiation coming from star formation. And if it's up here, it's dominated by radiation coming from AGN. So it's the same technique that many people the world over use to identify AGN. So we color code our spaxels by whether they're star forming, whether they're composite, so a little bit of both, or whether they're dominated by the AGN. The two black stars here, just to guide your eye, they're the centers of the stellar nuclei. And so what we found very suggestive was that around both of the stellar nuclei, the radiation was being dominated by AGN. That was certainly suggestive, but it's not complete proof that you've got two AGN, because it could just be one AGN that's ionizing an extended region. So then we went to Chandra, we got director's discretionary time to do hard X-ray observations of these. It doesn't show up particularly well on the projector. There's a very bright source in the center, but there's a secondary X-ray source here as well. So this was a detection of a dual AGN with the KBC separation. So that was a fun case study to get us started with MANGA data. But then we really wanted to dive in and look at the merger sample. So this is work that's being led by a master's student with me at UVic, Mallory Thorpe. So what Mallory has done is to go through the MANGA data and visually identify late-stage mergers. So these again are what we call the post-mergers. So single galaxies characterized by these strong tidal disturbances. So what we wanted to do was to look radially in these galaxies as to where all the action was happening in terms of triggered star formation, changes in the metallicity. There were some predictions from the simulations for this already. So this is some older work by Jorge Moreno again, where he's looking at where in the galaxy, in his idealized merger suite, the star formation is happening. So the x-axis now is a little bit different. It's no longer galaxy separation. Now this is the radial distance within your galaxy. Okay, so right in the central region, so between 0 and 0.3 kpc, all the way out to the outer disk, 3 to 10 kpc. The y-axis is still measuring the enhancement in the star formation rate relative to an isolated control. So each of the lines on here, so there are red and blue lines, depending on whether it's the more or less massive galaxy in the pair. Each of these lines is the profile for one interacting galaxy. So there are 3 different mergers on here, so 3 different orientations, and then a primary and a secondary for each one. So what we can see, and this was a subset of a larger suite, just as a representative sample, what we can see is that it's very common in the simulations to see enhanced star formation rates in the center. That's an almost ubiquitous prediction from this suite. But in the outskirts, there's much more variation in the outcome. Some galaxies have modestly enhanced star formation even in their outer disk. But it's more common to have suppressed star formation in the outer disk. It's not 100% clear why this is. One proposed mechanism that Jorge made in his paper was that the gas that is being funneled into the center, triggering these starbursts, means that then you've depleted the gas reservoir in the outer part, such that the star formation is suppressed. But I think there could be other possible explanations as well. But the prediction, nonetheless, is that there is a large variety. So we need to develop a way to make these kinds of profiles for IFU data. So now I'm going to spend a couple of slides explaining to you the methodology that we developed in order to try to do this for the observations. Okay, so this is a diagram that shows the distribution for all spaxels, so all of those spectral pixels in manga. So this is not specifically for mergers. This is, you just take all of your maps of all of your galaxies and you plot the surface density of stellar mass relative to the surface density of star formation. So this has been called in the literature the resolved star forming main sequence. So in analogy to the global trends of total star formation rate and total stellar mass that we call the star forming main sequence, because this is on a spaxel scale, so these are measurements typically made on about a 1 kiloparsec scale. For that reason, people have been calling it the resolved star forming main sequence. Now this is a little bit misleading because we're not, of course, on a kiloparsec scale truly resolving star forming regions, but for better or for worse, this is the name that seems to have stuck. So this kind of distribution has been found since the early days of IFU surveys, for example, with Khalifa. So the discovery of this relationship is not new. I show it you here just to set the stage. So here is our resolved star forming main sequence for individual spaxels. So then what I can do is for any given spaxel, I can say, well, I know its stellar mass surface density. So I can predict from this line what its normal, if it behaved normally, what its surface density of star formation should be. And then if it's above that line, it has a positive delta sigma SFR, so it's star forming at a greater rate than I would expect for its stellar mass. And if it has a negative value, it is star forming at a lower rate than I would expect for its stellar mass. You can also match in other properties. For example, you can make sure you match your spaxels not just in stellar mass, but also in radial position, in bulge fraction, and total stellar mass as well. To not go into any of the sort of further nitty-gritty details, what you should remember from this is this delta sigma SFR is the offset in the star formation rate relative to what we would expect for a normal statistical spaxel. So to give you a sense of the way that we can use this statistic, here is a figure that, again, is nothing to do with mergers. It's looking at galaxies in general, depending on what their total star formation rate is. So to remind you, here is the global star forming main sequence that we've known about since the early days of large galaxy surveys like Sloan. Total stellar mass, total star formation rate, main sequence. So I can take slices above and below my star forming main sequence, such that when I'm well below it, I can kind of loosely call that a passive galaxy, and when I'm well above it, I could loosely refer to it as a starburst galaxy. So I'm going to take galaxies that globally are in different regions on this star forming sequence, and then look at their star formation rate profiles. So what that will allow me to do is ask questions such as, if I am a starburst galaxy, where is my star formation rate enhanced? Are these starburst galaxies globally enhanced everywhere in their disk? They have just really high gas fractions and they have high star formation efficiencies. Or is there some internal mechanism that's making them particularly star forming in the center or in the bar or in the spiral arm? All right, so then this figure is showing as a function of the radius within the galaxy in units of the effective radius or the half-life radius, what the profiles look like for that delta sigma SFR. So this is how far my spaxels are above or below the resolved main sequence. And this is a lot to process, and let me take you through it. So if I pick galaxies that are far above the main sequence, so at least a factor of 3 above the main sequence. So I'm going to loosely call those starburst galaxies, just for want of a better term. When I look at their radial trends, what I find is that their spaxels are on average above what I would have expected for that resolved relation, because they have positive delta sigma SFRs at all radii. So the star formation rates in these so-called starburst galaxies are elevated at all radii, at least out to about 1.5 effective radii. But the boost is highest in the center. So there seems to be a central peak in the starburst for these highly star-forming galaxies. Then you can step down through the main sequence. That's the color coding going from the colder colors to the warmer colors, until you're down in the so-called passive or the quiescent sequence, which is these galaxies that have got very low star formation rates down here. For those galaxies, which is the red line, we see basically the mirror image of the starburst galaxies. Their star formation rates are low everywhere, so they have negative delta sigma SFRs. And again, the effect becomes more pronounced the closer you get towards the center. So the passive galaxies are most strongly quenched in the centers, just as the starburst galaxies are most strongly star-forming in the centers. And so this seems to be some evidence for the regulation of both enhancement and suppression of star formation being centrally regulated. This just kind of orient you as to the kind of figures that are going to come next.
I think I remember that Erica Nelson had a paper a few years ago looking at a similar thing at high redshift 1 or 2, and I think she found kind of flat profiles.
Yeah, there's quite a long answer to that. She uses H alpha equivalent widths, which is a measure of specific star formation rate that has quite a shallow sensitivity compared to this. So she could not have seen this because she's just not sensitive to it. She also doesn't have these kinds of starburst galaxies in her sample. So all of her sample is kind of this middle region, which is quite flat. Now that's not to say there might also be something different happening at high redshift, but her sample, say, doesn't probe doesn't have the ability to probe this, and it doesn't have the sample size.
But also you said she uses like equivalent with which is specific star formation.
Yes.
And this is
This is star formation rate, but because we match in spaxel
I see.
mass, it's very similar. But if I were to plot on here Erica's kind of sensitivity threshold, it would be.
She also found in later work, I think, that they're underestimating the dust correction, that this could factor into it also. I don't remember the details. Yeah, actually, I had the exact same question, because the related thing is, so if we're, can you go back to the curve, for say, just pick a point, like for the starburst at the effective radius, like how many points are contributing in that bin?
Oh, tens of thousands.
Okay, because she did the stacking analysis, and so that factors in, you're sort of doing, so, okay, we can talk at dinner about the details.
Yeah. Which is, so because we have so many spaxels, so there are like 3 million spaxels in the data release. And so by the time you've sliced and diced it, you know, you've maybe got tens of thousands in each of these. But that's why these are so narrow in their width, because again, divided by Okay, so this is the methodology that we're going to use, but we're going to apply it now to the post-merges to see how those profiles measure up to the simulated predictions. So I already mentioned that Mallory had put together this sample of 36 post-merges from Manga. So in that sample, it's a small fraction of the total data release, a mere 20,000 spaxels to be working with. Here's an example of 3 of her galaxies. Again, I'm not quite sure how well the morphological features show up. And then these are the kind of individual maps we can make. So a map of the star formation rate, a map of the metallicity, and then maps of the differential properties. So I already described to you how we get this delta sigma SFR, but we can do the same with metallicity, because there's a resolved mass metallicity relation, just the same way as there's a global mass metallicity relation. So the way that this is color-coded is that white is no change, blue means boosted star formation, red means suppressed star formation. And then for the metallicities, the green means boosted metallicity, and the purple means suppressed metallicity. So the first thing you can see is there's quite a lot of structure, even in these 3 examples. Often the action is not just centrally located and then nice and smooth, and this really begs for a better approach than just radially smooth profiles. But for now, I'm just going to show you radially smooth profiles. So for the star formation rate, so here are the individual profiles. So each line here is an individual post-merges profile in this change in the star formation rate as a function of its effective radius. And the 3 bolded lines are the 3 example galaxies that were on the previous slide, chosen partly to show you some of the diversity in the sample. So we have cases where there's an enhancement in the center and a suppression in the outskirts. We have ones that are more flat. We have ones that sort of seem to change direction, partly because of this very clumpy offset nature that we see in the maps. So we can make a qualitative comparison to the simulations. We find that for the most part, the majority of the post-merges do have enhancements in the centers, and then there is much more variation in the outskirts. I suspect in the details it's not going to match this perfectly, not least because there are always caveats to go along with the simulations. But this is to show, I think, that there is this diversity in the outskirts, but a fairly coherent enhancement in the center. You can then average all of the spaxels from all of those profiles together. So this is what the average profile for a redshift 0 post-merger looks like. Actually looks very similar to what we found for the general starburst sample, which is an enhancement all the way out to at least around 1.5 effective radii, but then this central boost in the center. And we can do the same for the metallicities. Here there's, maybe there was a little bit of a surprise in the sense that the simulations would predict a drop of metallicity that is most noticeable in the center. So we do see low metallicities throughout. So again, this is the average profile for all of the 40-some galaxies. But there maybe is a turn up here. So this is maybe tempting to interpret as a maybe re-enrichment, but there are other possible less physically exciting reasons that this might happen as well, which I can talk about, but they're basically data and bias driven rather than physics mechanism driven. So this work was all published earlier this year in this paper led by Harry. All right, so let me summarize. So many of the predictions that simulations make about the properties of mergers, both in the pair and in the post-merger phase, have been now, I think, clearly demonstrated in the observations. So we see high star formation rates, we see diluted metallicities, and we see high AGN fractions. The one thing that I think there is still some tension, maybe, with at least some of the theoretical predictions are these gas fractions. There doesn't seem to be this large-scale blowout that was predicted at least in the early simulations, and both the atomic and the molecular gas fractions are enhanced by factors of around 2 to 3 in both the pairs and the post-mergers. And then finally, starting to look at this in a spatially resolved sense with the IFU surveys like MANGA, we're starting to really be able to trace these properties throughout the galaxy.